call this section 7.4, although there actually isn't a section 7.4 in your textbook. I thought I'd throw this in, especially for those of you taking AP Calculus. You'll see this very soon, or you've already seen this. We're going to talk about something called the natural exponential function. And to introduce this concept, I'm going to go back to something that you've seen before. Those compound interest type of questions from, I think, 7.3 and section 7.1. Okay? Hope you remember doing those questions when they say, okay, I've got this much money, this much interest, compounded annually, semi-annually, whatever, and we're doing it for 5 years. How much money is there after the end of 5 years? Those type of questions. Okay? Now, I've tried to generalize this in the formula here, where I said in general, if you have P dollars, and that's what you deposit into an account, that's your starting amount or your principal, okay? And it pays you an annual rate of interest, and I used R instead of I here, but it doesn't matter. R for standing for rate of interest. Don't forget R must be a decimal, so don't put it as a percentage. And then you're compounding that amount n times per year, so that's where you do semi-annually, n would be 2, monthly, n would be 12, and so on. And then after t years, well, the account will have what I call A dollars. A, of course, is just the final amount. Okay? And the formula that we looked at last time, A equals to P bracket 1 plus R over n, all close the bracket raised to the power of n times t. Okay, that's that compound interest formula. So, let's look at example number 1. Okay, after winning the $1,000 school scholarship, John decides to deposit this money into an account that pays an annual interest rate of 10%. Okay, so how much money would he have if he decided to keep it in the account for, let's say, 40 years? So let's pretend that at the age of 17, he gets this money and he leaves it in for 40 years. So when he's 57, let's see how much money he has if the interest was compounded annually. So annual interest just means that the n value equals to 1, right? N equals to 1. So A equals to P, which is $1,000. So I'm going to replace P with 1,000. 1 plus the interest rate is 10%, so 0.10. And because this is annually, I'm dividing it by 1. And then 1 times 40 is just, I guess, 40. Okay, I'll simplify this. That's just 1,000. 1.1 to the power of 40. And I don't know how to do this, so I'm going to bring up my calculator. And my calculator hopefully will help me calculate this. Press on. You do the same with your calculator, please. 1,000 times bracket 1.1, close the bracket to the power of 40. And, whoa, $45,259.26. Wow. 4,5,259.26. That's a lot of money. So once again, I'm getting interest once per year, getting an extra 10%, and then this is compounding because that extra interest I put back into the account, and it's going to grow, 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 grow. 40 years later, it's grown to $45,000. Well, what happens if we compound it quarterly? Same idea, except in this case, 1,000. 1 plus 0.10, but we're going to divide that by 4 this time. And since there are 4 different times in 1 year that we're going to get some interest, that means we're going to get this interest 4 times 40, or I guess that's 160 times. So 1,000, 1.025 to the power of 160. And let's see what that equals to. 1,000 times bracket 1.025, close bracket to the power of 160. A whopping $51,977. Wow. Hey, that's a big difference, isn't it? I think it was 87 cents. Wow. I mean, same time period. It's just one was compounded quarterly. I get interest every 3 months, I guess. That's quarterly. The other one, I'm going to get interest once a year. But look at the difference in money. It's like almost a $6,000 difference. Wow. So this is the effect of compounding at different times or different rates. Compounding once a year is good, but if you compound more frequently, it's much, much better. Okay? Now, my question to you to try to introduce this thing called the natural exponent is, what do you think would happen if interest were compounded daily? Or even better, even hourly. And my question is there a limit to how much interest can be earned? So let's find out, okay? Instead of using $1,000, because the number is really big, I'm going to use $1, okay? So suppose $1 was deposited in an account. And I guess the maximum interest you can get would be doubling. So let's say the interest rate is 100%. You will double your money, okay? Add the 100% to your original 100%. That's 200%. That's double, okay? So let's figure out how much money you would have after 1 year if you compound it n times. Now, n is something that we're going to change, okay? And we're going to use this table underneath to kind of help us figure this out. So remember, I'm depositing $1, so that means my principal is 1. Interest rate's 100%, therefore R is also 1. Okay, and if I have that, then that simplifies to 1 plus 1 over n times n. And because t is 1 year, that exponent just becomes n. Okay. Now, if it was 1 year, I'm going to take this formula now. 1 plus 1 over 1 to the power of 1. That seems to be just 2. So if I compound just once a year and I have an interest rate of 100%, it's going to double. Okay? Makes total sense. Okay. Now how about 12 months? So 12 months means I'm going to take that 100% interest and split it up into 12 different intervals. Okay, so 1 plus 1/12. So the interest is 0.083, I think. Okay, I'm going to raise that to the power of 12. So let's do that. Bracket 1 plus 1/12, all raised to the power of 12, and you get $2.61, 2.61. Okay, 2.61. So notice the effect of compounding here, even monthly. Okay, getting smaller pieces of interest, but I'm getting it earlier on so that it has more time to reinvest and make more money. So that $2 became $2.61. Well, what about 365 days? Let's say I get interest every single day. Okay, that should maybe make me more. So let's do that. 1 over 100, 365 to the power of 365. Okay, back to my calculator. 1 plus 1 divided by 365, all raised to the power of 365. 2.71. Okay. 2.71. Even more now. I made an extra 10 cents. Well, let's see what happens if I do it every hour. Now, how many hours are in a year? If we're assuming 365 days in a year, then 365 times, I guess that'd be 24, because there's 24 hours in a day. That's 8,760. And once again, that's just 365 times 24, right? So 8,760 hours. Okay, so 1 plus 1 over 8,760 to the power of 8,760. Okay, let's see what you get. Oops, I can't type into my calculator. 8,760, power of 8,760. And I get 2.718. So now I'm going to keep more decimals now, okay? 2.718126. 2.71826. Okay, I'm going to keep a few more decimals. Maybe I'm going to go back the previous one, 2.714567. Okay, so 4567. Just so you can see the increase here, okay? All right, now let's take a look at what happens if I go even further and say, let's do some compounding every minute. Since in an hour there are 60 minutes, I'm going to take 8,760, multiply that by 60, and what do I get when I do that? 8,760 times 60, 525,600. And if I were going to use this now, so 1 over 525,600 to the power of 525,600. Let's see what I get. So bracket 1 plus 1 divided by 525,600, all raised to the power of 525,600. How about 2.718,279? So 2.718,279. All right, and I guess I can go even further, and let's say this happens every second. That's nuts, but let's try. 525600 times another 60. That, I believe, will be, whew, getting big, times 60. How about 31,536,000 seconds? And if I were to now do that, let's see what magnificent number I get. 1 plus 1 divided by 31536,000 raised to the power of 31536,000. Huh? Oh, I left off at 0. 0. There we go. 2.718. So let's write this in 2.718282. Let's leave it like that. Okay? Now notice that as we continued and compounded more and more frequently, we started at $2 and we kind of ended up around 2.71828. Okay? So it looks like we leveled off around 2.71828. Okay? Now, if compounding, of course, would be done even more frequently by letting n become larger and larger, we have a special term for this. It will be called continuous. I can't spell. Continuous compounding. Continuous compounding. Continuous is like happening all the time. Every millisecond, something's going on. And for those of us in calculus, you have seen this notation before, the limit as n approach to infinity of the function 1 plus 1 over n, all raised to the power n. And this lovely expression just equals to this number, 2.71828,128. And this value is so important in math that it actually has its own symbol. It's called the letter E. And there's another symbol that we learned before, kind of like pi. So E is very closely related to pi because both of these decimal expansions never terminate nor repeat. And what we call these functions or numbers are, we call them irrational. So if you're curious on how you actually figure out E on your calculator, you can actually go to your calculating screen, okay, clear it, and I'm going to ask you to just take second function of the ln button, which gives you the e with an exponent. And if I want e by itself, that's e to the power of 1, and I press enter, you get 2.71828,128. Okay? All right, let's turn the page. So where are we going to use this now? Okay, so here's example number 2. It says, after winning the $1,000 scholarship, Jane decides to deposit it into an account that pays an interest of 10%, but this time it's compounded continuously. So how much would she have if she decided to keep it into the account for 40 years? Okay, so remember, what we've just done now is we replaced this whole part here, okay, almost this whole part, with the actual function e, but because you have a r as an interest rate, not just 1, this now just becomes the following. A equals to p, and that part becomes e to the r, okay, and then t. Okay, so that e to the r is equivalent to this whole part here. Okay. Now, using this lovely new formula, I can then figure out how much she'll have at the end of 40 years. So 1,000 e to the, and since r is the interest rate, we're going to keep this as a decimal. That's 0.10 then, and then t is 40, so I'm going to take it and multiply it by 40. That's the same thing as me saying 1,000 e to the power of 4, and on my calculator now, 1,000 times e, which is second ln, and then type in the 4, close the brackets, I'll have $54,598.15. it 54,598? Sorry. 54,598. 54,598. Eraser, please. 54,598.15. So $54,598.15. Okay, that's probably as much as I can get. Now, continuous compounding or compounding continuously can also be seen in population growth. Okay, as the population grows, we sometimes say it continuously grows. Why? Well, compounding annually, if I use that term annually, would mean that all the births and deaths occurred on December 31st of each year, right, at the end. But if compounding was done quarterly, that means all the births and deaths occur at the end of each quarter. That'd be March, June, September, and December. But of course, births and deaths occur continuously throughout the year. So, compounding continuously is really a very natural way to model large populations. And thus, instead of using 2 to the power x or 1.02 to the power x, we have this lovely equation, y equals to now e to the power x. And this equation is often called the natural exponential function. Okay? E to the x is the natural exponential function. All right. So I'm going to ask us to do this question now. Example number 3 says, in one recent study, E. coli bacteria was capable of doubling in number about every 49.5 minutes. Now, their population, that's P after T minutes, could be modeled by this equation, okay? N of T, which equals to N0 e to the 0.014 T. I guess what I'm saying here is that this whole thing here equals to the population, and there's your T, and N0, of course, is your initial population. So in this case, it says, suppose initially there are 500,000 bacteria in a sample. Determine the number of bacteria, not that bacteria present after 99 minutes. So if I use that formula, N of T, which equals to the population, I'll take N sub 0, which would be 500,000. I'm going to raise it to E, or times it by E to the power 0.014. So this is my, I guess, compounding or continuously growth. And continuously growing at a rate of, I guess, 1.4 seconds. Not 1.4 seconds, 1.4%, I guess. And raise this to the power of T. And T, I guess, is just 99 minutes. So we'll plug this in, we'll see what we get. I'll go ahead and use the calculator right away. 500,000 times E, second ln, 0.014 times 99, close the bracket, and I get what? Well, 1999. So what's that? Almost 2 million, I guess. So 1999 411.36. So I guess that's pretty much close to 2 million bacteria present. Okay? So, there you go. Now, as an extension, before we leave this, I want you to do example 3 again. But this time, don't use their equation of the E thing. I want you to solve it like you did before in section 7.3. Okay? So, remember, this is the doubling and all that stuff. We can have a formula that we use. Y equals to A. I like this one. C to the power of, I think, X over T. Remember that one? And I want you to use this formula. I want you to calculate what this is. And then I want you to notice what this E to the power of 0.014 actually equals to. Okay? Using our info from before. A, which is our initial amount, is 500,000. C in this case is our rate. And because it says the population doubles, it is 2. And since the time here is 99 minutes, 99, but the T is the time it takes for one rate to occur, or one cycle of the rate to occur, that's 49.5 minutes. So we'll get this now. 99 divided by 49.5 is just, I think, 2. 2 squared is just 4. And that gives me my 2 million. So pretty close to what I had from above. Okay. just a little bit off. And so I think these two things are exactly the same, okay? Pretty close, okay? Same. And so ultimately, I think what we can conclude about what this e to the power of 0.014 really is, remember that e is continuous growth, okay? The rate of continuous growth. So from e to the 0.014, we get here a continuous rate of growth of 1.4%, okay? And this seems to be equivalent to, so this is equivalent to well, it's equivalent to doubling every 49.5 minutes, right? Because ultimately, what we're doing here is 2 to the power of 1 over 49.5. And that should be the same thing as e to the power of 0.014. Okay? Let me just quickly show you that on the calculator, and then I'll be done this section. Okay? So, ladies and gentlemen, I just want to show you this idea of e. And I also want you to be aware of it, because it does happen quite a bit in the natural life sciences, especially with population growth of anything, whether it be people, humans, bacteria, or even money in terms of the financial part. Okay? So e to the power of 0.014, we have now 2 to the power of 1 divided by 49.5. And lo and behold, pretty much the same thing, 1.014. Okay? And that's where you get that compounding continuous percentage of 1.4%.